Sketch the curve with polar equation r equals 2 cos theta. We're going to start by treating r and theta as if they were Cartesian coordinates, and we'll graph the curve, 2 cos theta. So it oscillates between plus 2 and minus 2, crosses at pi over 2 and 3 pi over 2. There. And now our goal is to use that curve to construct a plot of the polar equation in the xy plane. Start by looking at this portion of the curve here. As theta increases from 0 to pi over 2, when theta equals 0, r is 2. When theta equals 0, r is 2. Then, as theta increases to pi over 2, the value of r decreases to 0. As theta increases from 0 to pi over 2, the value of r decreases to 0. So we may get something like this. I've drawn a semicircle, although it's not immediately obvious that the curve should be a semicircle. Let's use a table of values to help us understand the picture better. When theta is 0, r is 2. When theta is pi over 6, pi over 4, pi over 3, r is root 3, root 2, and 1. Again, not obvious that the curve should be a semicircle, but we're getting a better picture. When theta is pi over 2, r is 0, as we've noted. Now look at what happens as theta increases from pi over 2 to pi. The value of r decreases from 0 to minus 1. This is where things get a little tricky. When theta is 2 pi over 3, 3 pi over 4, and 5 pi over 6, the values of r are minus 1, minus root 2, and minus root 3. What does that mean for the picture? Here are some rays corresponding to angles of 2 pi over 3, 3 pi over 4, and 5 pi over 6. Because r is negative, it means that the point is going to lie in the opposite quadrant. So for this ray corresponding to angle 2 pi over 3, r will in fact, or the point, because r is negative, will in fact be down here. For this ray corresponding to angle 3 pi over 4, the point will be in the opposite quadrant, and same here. So the curve may look something like this. That wasn't very good. Here's a better one. And when theta is pi, r is minus 2. Again, here's a ray corresponding to angle pi. The point will be in the opposite quadrant, and r is at a distance 2 from the origin. Now let's continue on and look at what happens as theta increases from pi to 3 pi over 2. r starts at minus 2 and increases to 0. So for angles 7 pi over 6, 5 pi over 4, and 4 pi over 3, r takes on the values minus root 3, minus root 2, minus 1. Here are the rays corresponding to those angles. Again, because r is negative, the points will lie in the opposite quadrant. In fact, there'll be these points here. And so that first portion of the curve gets doubled up now. And similarly, as theta increases from 3 pi over 2 to 2 pi, r increases from 0 to 2. And now r takes on positive values, and so you don't have to worry about putting the points in the opposite quadrant, and I'll leave you to fill in the details if you wish. So what we've seen is that we have a curve that loops around twice. Now I've drawn the curve as a circle. This sort of exercise with the table of values can convince you when r is increasing, when it's decreasing, and so you get a general sense of the curve. But to see that it actually is a circle, you have to work with the polar equation itself, and remember that x is r cosine theta, and y is r sine theta. And so in particular, looking at x equals r cos theta, you could say, all right, x over r is cosine and theta, and so the polar equation is really saying r is 2 cos theta, or 2x over r, which could be rearranged as r squared equals 2x. But remember that r squared is x squared plus y squared. So this equation in variables x and y is x squared plus y squared equals 2x, which can be rearranged as follows. And if you complete the square, you get x minus 1 squared plus y squared equals 1, a circle of radius 1 centered at the point 1, 0. And there's an extra nice little argument you could make. This triangle is a right angle triangle. This side is r, this angle is theta, the hypotenuse is 2, and so the cosine of that angle theta is r divided by 2. In other words, r equals 2 cos theta.